Okay, for B, determine the average current in the primary winding of the transformer. Just now we already know that the current in the secondary is 12 ampere. What about the primary winding N1? So I1 N1 equal to I2 N2. Voltage times current over here ideally is the amount of voltage and current transferred to here. High voltage, low voltage, high current. So it becomes high current, low voltage here. Okay. So I1 equal to I2 N2 divided by N1. So you put in the values that we have obtained just now. So 12 times 533 divided by 240. So you will get 26.7 ampere on the primary. So we can see that the primary low voltage, high current transfer into the secondary of high voltage, low current. So 12 ampere here, 533 volt. Meanwhile, the primary or input 240 volt, 26.7 ampere. Okay. So this is the discussion for question 1 and 2, tutorial 1, tutorial 2. Okay, next we go to the example number 2. Okay, now we are discussing the example of circuit with a semi-control device. Means that the formula is normal per the uncontrolled device using diode just now. We are using now the SCR, silicon control rectifier. So the question is that design a circuit to produce average voltage at the load of 40 volt output from input of 120 volt RMS. This is average output. Meanwhile, the incoming is RMS 60 Hz with the load of 100 ohm. So we need to determine the power absorbed by the resistance and also the power factor of the circuit. Okay, means that when you involve with the semi-control circuit like this, first thing you need to find is the alpha, is the at what point of triggering angle you need to trigger or firing angle such that the output will remain at 40 volt. We reduce or we chop down 120 volt RMS down to 40 volt average at the output. So find alpha. So V out is equal to Vm divided by 2 pi 1 plus cos alpha. This is formula for half-wave rectifier using semi-control device. So V out is here given already of 40 volt. So V max have to times Z2 because here given in RMS. So 120 volt times Z2 divided by 2 pi 1 plus cos alpha. So you rearrange the formula. So 1.48 equal to 1 plus cos alpha. So you put the alpha on the other parts at the side. So you get alpha equal to cos of 0.48 becomes 61.3 degrees. Or you put in radian. So it becomes 1.08 radian and 0.7 radian. So how to convert from degree to radian? You just times pi divided by 120 and 180, sorry. 61.3 times pi divided by 180. So it becomes radian. So you have to be careful because once you calculate in radian, you have to change your mode into radian. Instead of degree, you change it to radian. Okay. So B, what are the power? So P equal to V square over R. It's the same. So V RMS here. So VRMS of this half-wave semi-control circuit is equal to VRMS equal to VM divided by 2 times 1 minus alpha over pi plus sine 2 alpha over 2 pi cert. So we can actually use two approach by using formula or by using PE curve. We'll learn about PE curve on the incoming topics. But for this exercise, we proceed with formula first. So we put in all the values. 120 volt peak times cert 2 divided by 2. So we put in the alpha in radian. If you key in or you set your calculator as radian, so key in radian. If you set as a degree, so key in degree. So you get 84.85 times cert of 0.793. So it becomes 75.6 volt in terms of RMS output at your Vout. Then your P is equal to VRMS squared divided by R. So 75.6 times squared divided by 100 become 57.1 watt. So what about the power factor of the circuit? So power factor equal to P over S. So P we have calculated 57.1 watt. What about S? S is the amount of input voltage RMS, which is 120 volt, times the current. So current you have to divide the amount of P divided by resistor. So 120 volt, we have here V divided by R. We have 75.6 volt divided by 100 ohm. So that's the current flows into the circuit. So we have 0.63 of power factor of this circuit. Okay, we have done discussion on the examples and tutorial for part 1. So we go into a little bit discussion on the lab that we have done on part 1 and part 2. For the simulation that you have done by right, this is the appendix that attached to the lab sheet. And ideally, if you run your circuit, this is the kind of waveform pattern that you should able to gain from the simulation. Okay, in terms of output attributes or values, so for your rectification, means from AC to DC, so the most meaningful output is in terms of average, because we are generating an average output voltage and also current. And for R, L and C, we shall see the difference in terms of their output. You can see that we have values for RMS for all the circuit, R, L and C. But in terms of power for your resistive, sure we have value, but for inductive and capacitive, there is no power that being absorbed, because inductor and capacitor, they don't consume power, and they just store and release the power. The consumable element is only R. So you deliver power to the R, so it will absorb and convert into energy. But for capacitor and inductor, it does not does not absorb any energy. So why the average value is important? Okay, because we are converting into DC. So DC can be measured in average. After we rectify and we filter out, so it will be in average DC. And also DC is referred in the datasheet. Let's say if you look at this diode datasheet from any of the reference. So you can see that the average value is equal to the amount that we integrate between 0 to maximum time of duration period. And so it will convert, it will refer as average current to compare in terms of how much the dissipated power of the device. So this one mentioned in terms of average current in terms of duty cycle. In terms of DC, fully conduct all the time. So this is the dissipated power or heat that will emit by the device. But if its duty cycle is only 50%, 0.5 or lesser, 20% or 10%, so this is the trend or the amount of current that it can conduct compared to the amount of heat or losses that emit or produced by the device. So all referred in average. And also we have also RMS, but RMS value is applicable for AC and AC output, or for the semi-controlled device. But for the uncontrolled device, almost we refer as average. Okay, we have also complex waveform. This is what I mean by duty cycle, how much the time on compared to the whole cycle of one cycle duration. So this is the cycle, time on over the whole one cycle of duration. In terms of form factor, is the amount of magnitude compared to the overall period. We shall see this one later. This is crest form factor. This is the attributes or the amount, the values that mentioned in the datasheet, and you have to actually understand, because it will be used in the certain design of our circuit. Okay, the power, the amount of I times V, the I that comes into the network or system, times the terminal voltage delivered to the system. Okay, instantaneous power means that the values at an instant, any point. So instantaneous power. AC, meanwhile your AC value will vary with time. Or average, no, this is the AC. This is DC, this is AC. So phasor is not vectors actually, because we are not dealing with the magnetic circuit here. So phasor actually representing V and I, normally in RMS value. So if you have a V and I here, and we refer the peak point V I as a reference angle from this blue curve here as reference. So the displacement angle is equal to angle of V minus angle of I. Okay, this is the average power. This is what I want to show you. When we deal with resistive power, so the P will be positive, always positive, because we have here I and V at the same phasor or same side. Positive will be positive. Negative times negative will be positive. But in terms of inductance and capacitance, you can see that this is positive, while this is negative, positive. It becomes positive and negative, so both will cancel, so you shall have your average power of 0. Same goes to the capacitance, positive and negative at equal, so average will be 0. So that's why when you run your lab, you shall have the values of P average of 0. Okay. Okay, for part 2 in your lab 1, so all of here you can find from the datasheet. either by calculation or by